So, good afternoon, and welcome to Wednesday, not Thursday, unlike I said on the video. So today we're starting magnetostatics. I warned you that magnetostatics and magnetism, there are way more cross products flying all over the place, and one of the fundamental reasons for that is that it's a purely relativistic effect, and it has to do with moving charges rather than stationary charges. So electromagnetism, electrodynamics, it's a very tightly constructed framework, which means that it's very hard to find a natural point in where you could kind of like start taking it apart. Hopefully you've been on this journey a couple of times already, because I know certainly the CSUN undergrads, you've had E&M 3 times. So you've probably seen the E&M taken apart a couple of times already. So hopefully you're not thrown off by the fact that we're going to do things a little bit differently today. But we have to start somewhere. So traditionally, magnetism, you could start it at the Lorentz force law. You could start at Biot-Savart. You could start with Ampere's law, and of course, all these things are intimately related because that's the entire point. But we have to start somewhere now. So today we will start with a simple dipole model of how two magnets interact. It's a little bit of a different approach than you might have seen, but I think it's a neat approach, and we'll see if we can do good job of showing you the way through the material when we come in from this angle. So the reason we're doing this with dipoles is twofold. First of all, we just wrapped up the multiple expansion, and a lot of the expressions that we'll start with today actually look very similar to the dipole expressions that we saw at the end of the previous chapter. So it's just swapping out your E's for B's. It's a straightforward change. Okay, so dipoles. The reason we're doing this with dipoles is, of course, also that as you now should know, that there's no such thing, as far as we can tell, as a magnetic monopole. So therefore, the next logical step as well, can we talk about the infinitesimal dipole? What do we mean by an infinitesimal dipole? Basically, we're saying there's an object that has a north and a south pole, but they're infinitely close, such that you can't break it up. And if you want to look at it in terms of charge, it's actually always neutral, but it's because the north and south pole are just, basically sitting on top of one another. And in that sense, it mathematically very naturally maps onto the electric dipole, where you have, one charge here and another charge there. So that's why we'll do that as the next step. All right, so we are talking about the magnetostatics. So we'll start with the basic interaction between two magnetic dipoles. Magnetism, the dipole is the natural starting block. So we have one dipole here, and then we have another one here. And then, so let's call this M1, and let's call this M2. And they are both infinitesimally small. We're just pointing them this way. And then there's some kind of a vector that points from wherever the origin is to R1, R2. And then of course the, by definition, is the difference between those two position vectors is the vector that's joining R1 and R2. Okay, now we are starting with the dipole-dipole potential interaction. So just gonna write it down. So it's the potential energy, and it's related to, first of all, that first dot with the second magnetic moment, and then M1 dotted with R21. Oops, there's a unit here. And then there's an M2 dotted with R21. And it goes like R21 cubed. So note that I factored out an R21 squared compared to what the book does. And that means that I've made these into unit vectors. So let's look at some limiting cases. So for instance, if we have an M1 and an M2, and let's say that they are both perpendicular to that R21. All right, so they're perpendicular to both perpendicular to their to that vector that's joining it. Well, in that case, let's say there are really only two ways. There is an M1 that is pointing like this, and an M2 that's pointing like this, or there's an M1 pointing like this and an M2 pointing like this, right? So same direction or opposite direction. All right, so case one, so your M1 and M2, I'll see my color coding is already messed up. So that's M2, M1. Anyway, they're different. So yeah, M1 here is green and it's M2 here, that's green. Anyway, it is what it is. So if they're anti-parallel, that means that this dot product, this M1 and M2, it's negative. And the M1 is perpendicular to R21 or R21, and M2 is also perpendicular to R21. So this term vanishes and this term vanishes as well. And so all we're left with is this dot product of M1 and M2. So our U is M1 M2 over R21 cubed with a minus. All right. In this case, they're pointing in the same direction. We're just flipping the sign of one of them. So we'll have an M1, M2 over R21 cubed. Okay, now, so between these two, it's obvious to see that this is not a preferred orientation because this one has a lower potential energy than this one. So that works out. And now the other extreme case would be if your M1 and your M2 are actually along the direction of R21. Oh, now I'm using uppercase. Okay, so what does that mean? Well, we're making this one go in this direction and this direction, and then the same direction or the opposite direction. Okay, so if your U is, in this case, your M1 and your M2, they're pointing in the same direction, so that dot product is M1, M2. Now, M1 and M2 are both in the direction of R21, so that means that this is M1 times the unit length of the unit vector, so that's M1, and this is also M2 times the length of the unit vector, so that's M1 and 2. Okay, so this is minus 2 M1 M2 over R21 2, 1 cubed. And similar logic, we're flipping one of them. Then that means that we're changing the sign here and we're changing the sign here. If we change M1, we're changing the sign here and changing the sign there. So all of these terms are inverted, so the entire expression inverts. So M1, M2 over R2, 1 cubed. Okay, now with these limiting cases in hand, we can start thinking about magnetic fields. So let's say we start with our M1, and we're putting it here, and then we're placing our M2 somewhere here. Now we're giving it some kind of an arbitrary direction. If we place it here, that is obviously not the lowest energy form, because this one is the one with the lowest potential energy, right? Because if the angle is anything other than exactly 180 degrees, this potential energy, you can see that from the dot products, this potential energy is bigger than if they're exactly anti-parallel. So actually here, we need this M2 to be pointing down. All right. Now, same thing here on the other side. If we put it here, then we actually need it to be pointing in this direction. And if we put it here, we need it to be pointing in this direction. So we can now connect these things with basically what are field lines. And they have these like kidney shape. And at anywhere here at that point, you should be able to figure out what the lowest potential energy configuration is. And that is the way that this M2 will look. So you should be familiar with this kind of construct. This is how usually magnetism is introduced. You know, you imagine that you're, traveling the world, and you have some kind of a compass needle, and you point it, and it points to the North Pole. But this is a different way of looking at it, and we started with a dipole, and now we're just studying the interaction between these two by having this M1 generate a magnetic field and placing M2 in it to probe what that field looks like, and we can see, there's a point up, down, left, or right. Okay, so the field and the potential energy, you can actually, if you look very carefully here, you can actually factor out your M2, right? So because you have an M1 here dotted with an M2, and you have an M1 with an R21, and now you have an M2 dotted with something else. So there's actually an M2 here that you can factor out. So I'm gonna put my M2 here. And now that means I can write this as M1 minus 3, M1 dotted with R21, and now times R21, but I'm leaving that dot product dangling because it's in front of the entire fraction. R32 combined, and then we need to fix the sign. So let's see. Yeah, I think I got the sign right. Yes, so that means minus and then plus. So this is therefore the magnetic field of one. You know, I'm using the wrong color. This is B1. Okay. So yeah, that's the field generated by M1. It is, of course, a function of the position that you probe this field in. So this is the it's a field that you place that second magnetic dipole in. So you can write this in shorthand. You could just write it as minus MB, where B is just whatever the field is, and M is the the thing that you place in that field to get the potential energy. Okay, for posterity, because I forgot to hit on pause. So this current carrying loop, place it in a magnetic field. We're going to assume that the loop is small. And now we want to calculate the torque on this loop due to the Lorentz force that's acting on this tiny square loop. All right, so how do we do this? So we start with, torque is always arm times F. What do we mean by arm? Well, arm, we just mean there's some kind of a pivot point. It makes sense to put that in the middle. And then the force on these 4 segments is going to be working with an arm of D that points from that pivot point, which is right in the center, to the point where the wire is. So we are decomposing this loop in 4 parts, right? And then we just get a D crossed with F. And then D is the arm, and then F is that Lorentz force. I made a comment earlier that IL, of course, they go together. L is a vector that points in the direction in which I is flowing. So that's why sometimes you'll catch me drawing it like this, because that's usually how I think about it. It makes sense to do it that way, right? Because that's really what velocity means, right? So there's a similar ambiguity here, except here we're talking about actual charged objects that just have some kind of a charge. So then we just get a D crossed with that F. Now that F is that Lorentz force. That's your 1/c IL crossed with B. We're assuming that B is some arbitrary B. And then we just need to fill in the blanks. So we're going to get 4 terms. All right, first one, that D1 is this one. That's pointing from here to there. In this coordinate system, that means it's pointing in the -y direction. So that's -y hat. And it's got a length of a/2 because the size of this loop is a. And then we're going to cross that with this dude. So that's 1/c I, and then we need to know what L is. For this one, the current is flowing in this direction, so that's the x hat direction. And the length is a, so then you get 1/c I a x hat. Now we're going to cross it with our arbitrary magnetic field. Now that's the contribution to the torque due to segment number 1. Segment number 3 is on the opposite side, and there are 2 things that change simultaneously. First, the arm's pointing in the opposite direction, and also the current's flowing in the opposite direction. So if the current's flowing in the opposite direction and the arm is pointing in the opposite direction, those 2 sign changes will cancel out. And sure enough, if you write this down, you'll find this is plus this term, and this is minus this term crossed with the same B. So in other words, that term for number 1 and the term for number 3, they're identical. Now, the same thing for numbers 2 and numbers 4, except here the arm is, of course, pointing in the x direction, so x. And then the wire has a current that's flowing in the y direction. And then number 2 and number 4, again, are each other's equal, because the arm to 2 and the current in 2 are exactly the opposite as the arm to 4 and the current in 4. So that means that this picks up a minus and this picks up change. Hang on a second. That becomes a minus. Yeah. So 2 inversions. That's also an inversion, but therefore it became a plus. Okay, this is an inversion, that's an inversion. So these 2 terms are the same. So we're going to get 2 times that term. Okay, so then we need to look at the actual cross products. First of all, the x hat with this x hat is going to drop out. So I'm going to throw this one out right away. And this y hat with that y hat, it disappears. Okay, then we have to look at x crossed with y. Now the x crossed with y becomes a z, and that z crossed with a y is going to give you an x again. So that works. But the x crossed with z is going to give you a y hat, and then we're crossing that with a y hat, so that disappears. So this z term disappears because y hat crossed with x hat crossed with z hat is 0, right? Because x and z also give you y. Same thing here. So you're going to get your y crossed with a z is going to give you an x, and then we're going to cross the x with the x, so that doesn't work. So we can throw this one out. So in the end, we are left with a rather surprisingly short equation. So we just need to figure out exactly what is happening here. So a a minus y hat crossed with, so let's make sure that we get our signs right, x crossed with y. Okay, so we're doing this on the side. So that's our y hat, x hat, and our y hat here. Now x cross y is z, and minus y crossed with z is minus x hat. Okay, so that's going to give you a minus x hat. And now let's gather our terms. We're going to get an a squared. The term becomes double, right? So because we have a half here and we also have an identical term underneath it, so that means that the 2 disappears. We have a current. We've got a current over C, in fact, and then we have a by times x hat. All right, I think I got all my terms. Let's make sure that I got them. So I got a squared, got my C, got my I, got my A, got my B. Yeah, we're good. Okay, so that's the contribution to the torque due to numbers 1 and 3. Contribution due to the torque of numbers 2 and 4. Let's do this. So our cross product we need to evaluate is x hat crossed with a y hat crossed with an x hat. Okay, now y crossed with x is a minus z, and x minus z is plus y, so that's y hat. So doing that on the side, so we're going to get a plus y hat, and oh, see, I have it double here, y hat. A squared I over C. Now there's a bx here, and I think I have got it. Yes. Okay, so what it says here is a squared over C times I, and then x hat by minus x hat by plus y hat bx. All right. Now, if we define the magnetic moment of this loop as, so we're going to say m, is that normal, and this is why I don't like using n for the torque, is that normal times a squared times I, then this is actually, oops, over C, then this is m crossed with B. All right, so now we've shown that the torque on something like a small current carrying loop gives you the exact same expression as the one that is derived from using the potential interaction between 2 dipoles. And of course, that's not really an accident, because microscopically, magnetism is due to the fact that there's tiny little currents that are circulating. Forgive me, of course, that doesn't explain why there's such things as spin 1/2, but that's all where it starts. Circulating currents give you magnetic fields. Okay, so now we have to talk about the generation of the magnetic fields for somewhat more interesting configurations. So we talked about the field due to a single dipole, but just like before, when we were doing when we were going from a point charge to a set of point charges, we have to figure out some way to generalize this to more complicated configurations. There are basically 3 ways to do this. One is to just take a bunch of these dipoles, figure out what all their fields are, and then just add them all together. That's the one that relies on the the one that relies on the superposition principle. The second one is to use Biot-Savart's law, which we will get to in a second. And the third one is to use Ampere's law. Now, let's try to get to Ampere's law first. So the connection is that we will try to cast finding this field in the same way as you would do this in electrostatics. So in electrostatics, there is a you don't use M's for dipoles, but you use D's. Then the E field due to a dipole is 3D some dipole dotted with R hat, and then R hat minus this D, same D, over R cubed. And then if we know that the E field is we know that it's minus the gradient of that potential, then you can invert this potential and you get D dotted with R. Let me write it just like the book. Oops, then there's a cubed here. Okay, so if you take the derivative of this term, you'll get this term. So we know how to get potentials, right? And then we get potentials by integrating over charge configurations. So, but instead of integrating over charge configurations, we're going to integrate over momentum, not momentum, dipole moment configurations. Okay, so we'll do the same thing, but we'll do this in magnetostatics. So we'll have some B, and that's the one that we had before. So that's our 3M dotted with R, and then R minus M over R cubed. And now we're going to call that, and this is a little weird, but we're going to call this the gradient of a potential. And this is now the magnetic scalar potential. Now, magnetic scalar potential is a little weird, and we usually don't use it because in the end, when you start taking line integrals through magnetic fields, turns out it's not as useful a concept as it is in electrostatics, and we usually use the vector potential. But for things like this that are, then this is a really, really useful concept. So then our phi of M is that same, sorry, I'm so used to writing it with Muse. It's this same potential. And then the question is, how do you find the magnetic field due to a current, some kind of a current? So let's get this going. So let's say where we have some kind of this is how we draw arbitrary. Okay, some kind of a current carrying loop. It's got a current I, and we know that for every infinitesimal section here, there's a little patch here for which we can say, if there was a current that is circulating in this direction, then we know what the magnetic moment due to that would be, because we just worked that out. The moment would be it would be I times A squared over C times the normal. So that's the this is M, of course. And then this is the actual normal. Okay. Now, the trick in the following is the following. So if we take, let's say, one patch over here, and then we take another patch and then we put right next to it, and we take the same orientation as for the current that's circulating. So it's going in this direction in this patch here, and it's going in this direction in this patch here. Then we know that we can add the magnetic moments due to we can add the magnetic fields due to these moments. So it makes sense to split up this current carrying loop into tiny little patches. But the question is, what do we do with these wires that have seem to have currents that are somewhere on the interior of this loop that are absolutely not present? So the trick is that you put all these patches together such that when this one is touching this one, where they are touching, there's no net current anymore. And you do that, and you set up a grid basically in your current carrying loop, and you build this grid out of infinitesimal patches that are giving you a magnetic field. And anytime this wire of this patch has a current that goes up, the one that is right next to it has a current that goes down. So you don't see any current here where these patches are touching, except for when they meet the edge of the structure where the actual current is flowing. So that's a beautiful thing. So that allows you to describe this process as something that you can integrate over, and then you don't even need to know. You don't even need to worry about all the interior currents. So then the question is, well, if we have this potential, then that means that the total potential would be that integrated, right? So instead of writing this as a potential due to a magnetic moment that is due to some macroscopic object, we're going to write it as an infinitesimal thing. So then that means instead of writing it like this, we need to actually integrate. And we'll integrate over those moments because the moments are all given by this. And rewriting it, you get this. That's your normal. And over r cubed, so it's just this expression. And now integrated over the surface area. And this is the differential form of this moment. I hope you see that. And then there's, of course, the I here and the C there. So we went from this discrete phi of m and this discrete m to this integral form of the field. Okay, now look very carefully what this thing is. So if you look at this, there's actually a I over C. And now I'll write this in a little bit different form. So this is r squared dotted with dA vector. Now, hopefully, you will have seen this construct before. When I teach my undergraduate course, this thing, this dA vector with this r squared, is the thing that allows you to build Gauss's law. And the thing to look at is to say that, well, if we have this thing that we're integrating, that it's like 1 over r squared, and we're integrating that over the surface area, that is as if we are integrating over part of the solid angle. So let me draw that. So there's a, let's say there's a point here. And then we have our loop here. And then from here to there, oops. So this is our R. From this point of view, which is where we are evaluating the potential, we are integrating over the surface area of this loop. And it is as if we're figuring out what that surface area is from this point of view, and that thing has a name, and that is the solid angle omega. So this is actually I over c times the solid angle seen from the point of view of the point where you want to know what the magnetic field is. So this becomes this is actually a remarkably simple expression. It just means that if you have a so take some point and you look at this, you can just eyeball what the solid angle is, and then you have I over c. That's your potential, and then you take the gradient, and then you get your field. Okay, now that's an important point. So now we have to ask ourselves, okay, what happens when we evaluate this as a function of b? So for instance, we're going to take a path, and we're going to take this path, and we're going to start somewhere here and go up, and we'll go out. We'll go out here, and then we'll end up back here. Okay, so at every point here, we can ask ourselves, what is phi? Now at any point here, we can ask ourselves, what is phi? Well, so imagine that you're sitting somewhere here, and you want to know what does that magnetic scalar potential look like? Well, you just look back and you say, okay, well, I see that this thing is takes up a certain kind of space in my field of view, and then therefore I know what the solid angle is. So at this point, you would have the solid angle like this, and that's your omega. Now, if we take this path and we go to infinity, at some point this circle, this loop is going to start look like a dot, and then as soon as it's a dot, it doesn't have any appreciable solid angle anymore from the point of view of the point where you're looking back at it. So potential goes to 0 at infinity. So this goes to 0 at r is infinity. And now, while we're at the edge of the universe, we go and we take a tour, and we go down here, and we still at infinity, but then we go through here, and we're still very far away. So even though we are crossing the plane of this loop, it's still a loop that is very far away. So we still cannot tell it apart from a dot. So in terms of the omega, it doesn't really, it doesn't look finite. And then we're going here, and then we're coming here. And now we are again looking and approaching this current carrying loop. And now we again see it grow in size, and then we can see that the solid angle changes. Now, there's something really, really weird that happens when you cross the plane here. So imagine that you're crossing the plane here, and let's say you're approaching the plane here, and you see this solid angle becomes bigger and bigger and bigger. And at some point, it is 2 pi, right? Because 2 pi is half of your field of view, right? You're right in the middle, and this thing takes up the horizon. So the solid angle is 2 pi. And now you go forward, and now you have to look back. And because you have to look back, it's not 2 pi anymore, it is minus 2 pi. So the moment you cross this boundary here, there's a jump in the solid angle of 4 pi. So there's a phi here, there's a phi there, and this one is infinitesimal amount above it, and this one is an infinitesimal amount below it, and the difference is 4 pi, and then expressed in terms of current, I over c. Okay. Now we have to ask ourselves, what is in fact the thing we're doing when we are looking at our scalar scalar magnetic potential, it is the same thing as in E&M, right? So in electrostatics, the difference in potential is the line integral of E over the path. So we can do the same thing here. We have a scalar potential, and we can say, well, that's the line integral of B over the path. So, all right. So let's call that. We know that it's 4 pi I over C, and it's the line integral over the path. So that's a B dl. And now, if this path is closed, then it is equal to this 4 pi I over C. And we know that this integral is independent of the path, which is a little bit weird. So you have to think about this a little bit. So we know that the integral is independent of the path. What does that mean? Well, it means that we can ascribe a potential to any point in space here and give it a unique value that depends only on the position in space. It does not depend on how you got there. Well, if you look at this potential, that is exactly what this thing is. This is always, no matter how you got to that point, you can always look back or in front of you and figure out how much space does this loop take up. And that gives you the solid angle. And then depending on whether you're above the plane or whether you're below the plane, you could get either a positive or a negative solid angle. And only when you cross the plane is when you get a little jump in that potential. Now, this is, of course, Ampere's law, which describes the magnetic field integral over some kind of a closed path generated by this current I. So that is the scalar potential at work. Later on in the chapter, of course, we will get to the vector potential, because that's actually also a really, really useful concept. But this is famous in its own right, and that is, of course, Ampere's law. There is actually another way in which you can which you can look at this. And if you take, let's say you actually want to get B, and it would be minus the gradient of that phi, the magnetic scalar potential, you can actually through some calculus kung fu, you can actually rework this integral into a line integral, and that is actually, it's a famous line integral, and that's actually the line integral for the law of Biot-Savart. So it comes from the same place, but you just do something different with it. So instead of working in the potential formulation, you actually are working in the magnetic field formulation. So that's our R, and then that's our R squared. And that is the law of Biot-Savart. Okay, so that's Ampere's law. Oops. And that is Biot-Savart. They're both useful. They're both useful ways of figuring out what the magnetic field is. This is an explicit integral over a current carrying loop, right? So you have some I that goes through the loop, and you basically need to integrate over that loop, and then you get the magnetic field. This is a thing that you can use in situations with a super high degree of symmetry, and then you can work out what the magnetic field is. So let's go over a couple of examples of magnetic fields. Any questions? Ampere's law at work. Ampere's law at work. Hopefully you've seen these kind of things before. I know I teach them in my undergrad class, but it's good to repeat these a little bit. So let's say we start with a torus, aka donut. So what do we mean? Well, we have some kind of a circle, and it's got a hole. It's a proper donut, and then we have a wire that is wrapped around. So it goes around. And the current's going in this direction. And in degrees of high symmetry such as this, we can just use Ampere's law, and we can take a path, our BDL, and set that equal to 4 pi I over C. And then in situations where we assume that B is the same across the entire path of that integration, you can factor out your B from your integral, and then you get a very straightforward situation. So if we do that here, so for instance, we're doing our contour, we pick our contour here, so that's C. Now if we pack these windings of all these wires, if we pack them really, really close together, then you can spin this donut around and it would always look the same. So in other words, we don't really expect this thing to look any different when we rotate it. So therefore, we also don't really expect the B field to change between this point and that point. So we're assuming that the B field is pointing in this direction along that line of integration. All right, so then in that case, we get the line integral of BDL. It's going to be 2 pi times whatever R is. So 2 pi R, let me see. Yeah, times B is going to be 4 pi I over C. Now, what is I? It's basically the I that pokes a hole in this surface. And it's, well, it depends on how many wires you've got. So it's 4 pi times, let's say it's n loops. So that's the number of loops or number of windings. I over C, and then solve for B. B is okay. Now you got your field. This is of course, example 1. Another famous example is what happens when you take a torus and blow it up, so that instead of this thing being round, it actually becomes infinitely large, and then you can zoom in on a section here that is basically straight, and then we are talking about a solenoid. So in that case, we have our wire all right. And now there's an important observation here. So there was no reason for the magnetic field to exist here because there is no, so B is 0 here. Because that current that is enclosed by this contour is 0. So therefore, we also don't expect a field here. So we only need to worry about the field here on the inside. So we take a path. Let's see. So we take a path here, and we do our integration in this way. And then we ask ourselves, okay, if the field is pointing in this direction, which it is, then because of translational invariance in this direction, we don't really expect the B field to change over the course of this part of our line integral. So this is going to give you a contribution to the line integral equal to L. So let's call this L. All right, so it's going to be B times L. And then here we are stepping outside of our torus. Now we don't need to worry about this transition too much. In fact, we can make this this section as small as possible, such that we don't have to worry about the contribution to that line integral due to whatever is happening here at this edge. And then when we're outside on our return path, our scalar potential is not changing, right? Because we're outside and B is the same. So that's just B times L. And that's equal to 4 pi I. Now I here is again I times however many we have over C, but now this is the number of windings in the contour. All right, so in this case it's 2, and if we're doing this in a super high degree of symmetry, we pack our wires really, really close. Then we can just say this, and then we get our B is 4 pi I over C, and then we have N over L. And now this is, of course, our winding density. So these are your general procedures. Now, a couple of things about sign conventions. So this I and this contour integral are linked through a right-hand rule, where the sense of integration is given by the fingers of your right hand, right? So if you're integrating like this, then this is what your fingers of your right hand do. Then your thumb is indicating a positive current. Sense of integration are your fingers, and then your thumb is I greater than 0. So that's how we know which way the field goes. Okay, so in this case, the sense of integration is given by the arrow on this pencil line. So that's what we mean by the sense of integration. So it goes, if we integrate like this, then we mean a positive current is going in that direction. And in fact, in this case, the current is actually going in the opposite direction, right? Because our thumb is pointing up, but the current's going in. So there's probably a minus sign here that I need to pay attention to.